All right. Eigenvalues and eigenvectors. Given a matrix A, with size n by n, we define an eigenvector of A as any vector x that is not the zero vector, such that A times x is equal to lambda x. This this symbol is the lowercase Greek letter lambda. So we say that this is called an eigenvalue. Well, first, let me write how this is written. You read this as lambda, the lowercase Greek letter lambda, and lambda is called an eigenvalue. Okay. Lambda can be a real or complex number. So in other words, we say that a vector is an eigenvalue. I mean, it's an eigenvector if when we do the multiplication, the matrix A times x, we get a constant or a real number or complex number times x. I mean, if this equation is true, then we say that x is an eigenvector. And by the way, lambda is called the eigenvalue. So for each eigenvector, we will have associated an eigenvalue, of course. But lambda is supposed to be a real number, or it can be a complex number. Example. Show that the vector 1, -1 is an eigenvector of A equal to 1, 3, 4, 2. So we have to show what? We have to show that A times x must be equal to lambda times equal to some real number or complex number times x. But notice what's going to happen here. We have A that is 1, 3, 4, 2, and x that is 1 and -1. If we do the multiplication, we have 1 times 1 is 1 plus -3. And here below we have 4 times 1 is 4 plus 2 times -1, -2. And this is equal to -2, comma 2. But notice this vector, -2 and 2, can be written as well as 2 times -1 and 1. You see? So what is the same? 2 times the vector x. So notice ax is equal to 2x. You see that? So we say that x is an eigenvector. Then x equal to oh, I'm sorry. I think I did a mistake. So we have here -2 and 2. And the, oh, I'm sorry. Yeah. This is -2 and 2. So I have to factor out a -2. -2, and here should be -1. So yes, we have -2 times 1, -2. -2 times -1 is +2. So -2. Yeah, I'm sorry. Then the vector x equal to 1, -1 is an eigenvector of A. And what is the corresponding eigenvalue? This -2. And lambda equal to -2 is an eigenvalue. So again, if we have a matrix A times a vector x is equal to, in this case, a real number times the same vector x, so we have an eigenvector, and the number and the real number in this case is an eigenvalue. But how to find the eigenvalues for a given matrix? Theorem. Lambda is an eigenvalue of A if and only if the determinant of A minus lambda times the identity with size n is equal to 0. Remember, this matrix is the identity matrix with size n, assuming that, of course, that A is size n by n. So how can we find the corresponding eigenvalues? We have to find a determinant of this matrix. Example. Find the eigenvalues of A equal to so find the eigenvalues of this matrix. Notice this matrix has size 3 by 3. First, we need to compute oh sorry, let me do it with this other color. We need to compute the determinant of A minus lambda I. In this case, notice how the size for this matrix is 3 by 3. So I need to compute, so here the identity matrix has size 3 by 3. Now, A minus lambda I3 is equal to 1, 1, 1, 0, 3, 3, negative 2, 1, and 1, minus the identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. And notice, always when you are computing this subtraction, you will have to subtract to the main diagonal. Well, I'm sorry. I need to multiply times lambda first. Lambda is a number, a real number. So in this case, we have equal to 1, 1, 1, 0, 3, 3, negative 2, 1, 1, minus. Notice how when you multiply lambda times this, we're going to have only zeros except in the main diagonal. So this becomes lambda 0, 0, 0, lambda 0, 0, 0, and lambda. You see? So if you do this subtraction, notice how only the main diagonal is going to be affected. So this is going to be 1 minus lambda, 1, 1, 0, 3 minus lambda, 3, negative 2, 1, and 1 minus lambda. You see? So now we need to compute the determinant for this. Determinant of 1 minus lambda, 1, 1, 0, 3 minus lambda, 3, negative 2, 1, and 1 minus lambda. You need to compute the determinant. Of course, you can compute the determinant by using a web page to multiply, to compute the determinants. No problem with that. But once you have computed the determinant, you are supposed to get this one. This is going to be equal to negative lambda cubed plus 5 lambda squared minus 6 lambda. And this, once you compute the determinant, of course, always you are going to end up with a polynomial in lambda, always, when you compute the determinant. Once you have computed this, once you have computed the determinant, you need to set this equal to 0. But first, this polynomial is called the characteristic polynomial. Characteristic polynomial. So now set this equal to 0. We have negative lambda cubed plus 5 lambda squared minus 6 lambda equal to 0. And we have to solve this polynomial. If we solve this, notice how I can factor out the lambda here. So I have lambda times negative lambda squared plus 5 lambda minus 6 equal to 0. And this expression here inside can be factored as, well, this is lambda Oh, well, I'm sorry. First, I think I need to notice, I have negative lambda squared plus 5 lambda minus 6 multiplied at both sides, or here, I mean, I can factor out this negative sign here. So this implies negative lambda times lambda squared minus 5 lambda plus 6. You see, I mean, it's the same thing, equal to 0. Now, this expression can be factored in the next way. Maybe you remember this technique. Give me two numbers such that multiplied they are equal to 6, and when you add them, you have negative 5. Those numbers are negative 3 and negative 2. So this expression can be factored as negative lambda times lambda minus 3 times lambda minus 2 equal to 0. See? And now you can find the zeros if you set each of these equal to 0. So set this equal to 0, this equal to 0, and this equal to 0. You will have lambda equal to 0, lambda equal to 3, and lambda equal to 2. And of course, these ones are what? The eigenvalues of A. So when you have to find the eigenvalues for a given matrix, everything is going to be reduced to find the solutions or the zeros for a polynomial. That okay? For a polynomial, because each time you compute the determinant for this matrix, always you're going to end up with a polynomial. So this problem is reduced to solve a polynomial. Finding the eigenvalues is reduced to that. All right. So let me give a definition for that. If A is an n by n matrix, then the polynomial in lambda given by p of lambda equal to the determinant of A minus lambda I is called the characteristic polynomial. For A. Remark. The eigenvalues of A are precisely the zeros of the characteristic polynomial. This is the solutions of P of lambda equal to 0. So other example, find the eigenvalues of A equal to 1, 5, 3, 3. So again, we compute the determinant of A minus lambda, in this case, the identity matrix with size 2, because this has size 2 by 2. And as you noted before, as I have mentioned before, this is going to be only the matrix, the same matrix here, but for all the elements in the main diagonal, subtract lambda. And with that, you will have this subtraction here. So this is going to be 1 minus lambda, 5, 3, and 3 minus lambda. See? Again, when you do this subtraction, everything is reduced to, in the main diagonal, subtract lambda. Like we did it before, you see? This one. All right. So you need to find the determinant for this. So the determinant in this case can be computed, I think I can do it by hand. So it's going to be 1 minus lambda times 3 minus lambda minus 5 times 3, 15, you see? And so we have here 1 times 3 is 3, 1 minus lambda, minus 3 lambda, plus lambda squared, minus 15, and this becomes lambda squared, minus 4 lambda, minus 12. And again, give me two numbers such that when you multiply them, you have negative 12. And when you add them, you have negative 4. So this is equal to lambda minus negative 6 and positive 2. Yeah, negative 6, positive 2. And then set this polynomial equal to 0. Set P of lambda equal to 0. And we have lambda minus 6 times lambda plus 2 equal to 0, and this implies, again, set each of these equal to 0. This one equal to 0 implies lambda equal to 6, and this one equal to 0 implies lambda equal to negative 2. So we have lambda equal to 6 and lambda equal to negative 2. These are the two eigenvalues. There you have. Now, some properties for eigenvalues. The first one. Oh, I'm sorry. Let me write first the hypothesis. If we have a matrix with size n by n, and lambda is an eigenvalue of A, then part A. Lambda raised to the k is an eigenvalue of the matrix A raised to the k for k any natural number. 1, 2, 3. Property B. If A is invertible, I mean it has an inverse, then 1 over lambda is an eigenvalue of the inverse. And property C, if alpha is a real number or a scalar, then lambda plus alpha is an eigenvalue of the matrix A plus alpha times the identity n. Oh, there's one more. D. A and its transpose have the same eigenvalues. So these properties might be useful when we need to compute some eigenvalues. I want to point out the property number C. If we have any scalars alpha, then the sum of lambda plus alpha is going to be an eigenvalue for the matrix A plus alpha times the identity. Example. For the matrix we saw before, A equal to 1, 5, 3, 3, find an eigenvalue for A raised to the 3. Notice, this is the same matrix we saw in the previous example. In this one, 1, 5, 3, 3. We know this matrix has two eigenvalues, 6 and -2. We can choose the number 6. Well, but if you want to choose -2, no problem. But I'm going to choose 6. So find an eigenvalue for this one. It's simple. According to the property number part A, I have to raise only the eigenvalue to the k. So it's going to be eigenvalue for this one is only 6 raised to the 3. You see? Notice that since the determinant for A is 3 minus 15 equal to -12, that is not 0, then A has an inverse. But we don't have to compute the inverse. We have to find only one eigenvalue for the inverse. One eigenvalue for the inverse is going to be lambda equal to 1 over 6. Yeah? 1 over this one. 6 is an eigenvalue for A. 1 over 6 is an eigenvalue for the inverse. And part C, we look for an eigenvalue for find an eigenvalue for the matrix A times 2 times the identity matrix with size 2. In this case, it's very simple. Since we know that 6 is an eigenvalue for A, then one eigenvalue for this, notice, is A plus twice the identity matrix with size 2. This is going to be only 6 plus 2. That is equal to 8. And that's all. You see? All right. Now, once we have the eigenvalues, how do we find the eigenvectors? Well, we have to use the definition. Example. Find the eigenvectors for the matrix A equal to 1, 5, 3, 3. We know this matrix has eigenvalues lambda equal to 6. I'm going to call this lambda 1, and the other one lambda 2 equal to negative 2. So we have to find the eigenvalues for the eigenvectors for this. For the first one, lambda 1 equal to 6. We look for a vector x1, x2 that is not the zero vector, such that when we multiply a times x, we have, in this case, lambda 1 times x. And this becomes 1533 times x1, x2 should be equal to 6 times x1, x2. And notice, always when you are finding the eigenvectors in this way, we are going to end up with a system of linear equations, because this multiplication in this side becomes 1 times x1 is x1 plus 5x2, and 3x1 plus 3x2 equal to 6x1, 6x2. So I have these two matrices equal. So they are equal if and only if they are equal component by component. So this one has to be equal to this one, and this one has to be equal to this one. Then we have x1 plus 5x2 equal to 6x1. And the other equation, 3x1 plus 3x2 is equal to 6x2. You see? So it's always is a system of linear equations. But well, I have to modify this a little. So I notice that I can cancel this 6x1 if I subtract at both sides. So this is going to be x1 minus 6, negative 5x1 plus 5x2 equal to 0. Subtract here minus 6x1 and minus 6x1. And then we have negative 5x1 plus 5x2. And notice in the same, I can do the same for the equation number 2, negative 6x2 and negative 6x2. So this becomes 3x1 minus negative 3x2 equal to 0. So this is a system of linear equations. It's even more. It's an homogeneous This is an homogeneous system of linear equation. That means that in the right side for each equation, we have only zeros, 0 and 0 here. Notice this system, this kind of systems, an homogeneous system of equations always has at least one solution. That is going to be, if we choose x1 and x2 equal to 0 and x1 and x2 equal to 0, that means that always we're going to have at least one solution. But remember that by definition, an eigenvector cannot be this zero vector. An eigenvector with only zeros cannot be an eigenvector. So even when this system has at least one solution, if we want to be able to find an eigenvector, we will need to find more solutions, if any. Remember that any system of linear equations, as for the solutions, only happens three things. It has exactly one solution, it doesn't have solutions, or it has infinitely many solutions. Since an homogeneous system of equations has always at least one solution, then that means that that solution can be unique or there are infinitely many. So we need to investigate whether this has solution, infinitely many solutions, or only one solution. For this, how can we do that? Remember, we can find the reduced echelon form. Reduce echelon form. Go back to your notes in the chapter 1 if you forgot about this, but use the calculator that I recommended for you. The reduced echelon form for this system is 1, -1, 0, 0, 0, and 0. Remember, this column represents the x1 and this one the x2. So once you have the reduced echelon form, remember that we have basic variables or free variables. In this case, since the one that has only a 1 in its column is x1, x1 is a basic variable and x2 is a free variable. Again, if you forgot about this, go over the notes in the chapter number 1, I think. I'm sorry, I forgot the chapter or the section, but we have covered this. We have video notes and assignments for this reduced echelon form. So in this case, x1 is the basic variable. And x2 is a free variable. So from this equation, x1 minus x2 equal to 0. From this system, we can obtain back the system of equations. So this is going to be again 1x1 minus x2 x1 minus x2 equal to 0. So remember that we have to express the basic variable in terms of the free variables. So in this case, it's very simple. We have x1 is equal to x2. So then the solutions, the vector the eigenvectors have the form x equal to x1, x2 but this is equal only to x1 is the same as x2, so I can put only x2, or what is the same, x2 times 1, 1. You see? So notice that this implies infinitely many eigenvectors. How can I choose one? Well, just assign one number for x2. For example, if x2 is equal to 1, 1 times 1, 1, 1 is an eigenvector. If x2 is equal to 3, 3 times 1 times 1 is 3, 3, 3, 3 is another eigenvector, and so on. There are infinitely many eigenvectors because we have infinitely many numbers x2. So this is asked for lambda 1 equal to 6. We repeat the process, but now for lambda 2 equal to negative 2 for this one. Lambda 2 equal to negative 2. The same as before. We look for a vector. We look for a vector x that is not 0. Different from the 0 vectors such that a times x is equal to, in this case, lambda 2 times x. Or what is the same? A times x is equal to negative 2 times x. You see? The same as before. So this implies the matrix A is 1, 5, 3, 3 times x1, x2 is equal to negative 2 times x1, x2. And again, we're going to end up with a system of equations. It's going to be x1 plus 5 x2 equal to negative 2x1, 3x1 plus 3x2 equal to negative 2x2. And again, if we simplify this, we're going to obtain 3x1 plus 5x2 equal to 0, and 3x1 plus 5x2 equal to 0. So you obtain the reduced echelon form. Notice how actually we have the same equation, right? So of course, we're going to have infinitely many solutions. But anyway, the reduced echelon form is going to be this one, 1, 5 over 3, 0, 0, 0, and 0. So again, this corresponds to x1 and this to x2. So this means that we have x1 plus 5 over 3x2 is equal to 0. So this implies that x1, I'm sorry, I forgot to put that. Let me write it here. x1 is a basic variable. And of course, x2 is a free variable. And then x1 is, I have to express x1 in terms of x2. Is going to be negative 5 over 3 x2, so that the eigenvectors in this case in the form x equal to x1, x2 they're going to be equal to negative 5 over 3x2 times and x2 below. So you factor out the x2, we have x2 is equal to, x2 times negative 5 over 3 and 1, you see? So again, we have what? Infinitely many eigenvectors. So for each value of x2 that you assign, we have one eigenvector. For example, set x2 equal to 1, 1 times negative 5 over 3, 1 times 1, negative 5 over 3, and 1 is one eigenvector. X2 equal to 2, 2 times negative 5 over 3, negative 10 over 3, and 2 times 1, 2. Negative 10 over 3 and 2 is another eigenvector, and so on. Is that okay? All right. Definition. If A is of size n by n, and lambda is an eigenvalue of A, then the null space of A minus lambda times the identity with size n is denoted by E subscript lambda and is called the eigenspace. So the eigenspace is a subspace of Rn. So notice one remark. Remember, the null space is all the vectors x such that A minus lambda times the identity times x is equal to the zero vector. So the null space, I think we saw that before in some of the sections. The null space is subspace. Or B. So if it is a subspace, it has a dimension. Remember that? All the properties for subspaces can be applied here. And the dimension of E lambda is called the geometric multiplicity of lambda. All right, example. Determine the geometric and algebraic multiplicity of A. Given A equal to 1, 1, 0, 0, 1, 1, and 0, 0, 1. So first, we have to determine the eigenvectors. Remember, for the eigenvectors, we need to compute the characteristic polynomial. And this is, remember, the determinant of A minus lambda times, in this case, this matrix has size 3 by 3, so the identity matrix with size 3. So what is the same? This is equal to the determinant of, remember, I have to subtract only lambda in the main diagonal. So it's going to be 1 minus lambda, 1, 0, 0, 1, 1, 0, 0, and 1. Notice that this matrix is triangular, so the determinant is going to be only what? It's going to be, oh, I forgot to, I'm sorry. 1 minus lambda and 1 minus lambda. Yeah, this matrix is triangular, so the determinant is going to be only the product of the numbers in the main diagonal. So this is going to be only equal to 1 minus lambda, 1 minus lambda, and 1 minus lambda, or what is the same? 1 minus lambda raised to 3. This implies that the algebraic multiplicity of lambda is going to be 3. Oh, well, but I haven't computed this, I'm sorry. So, I'm sorry. Let me write this because I went one step forward. First, I have to solve this, right? So, this is the characteristic polynomial. This one. Now, first set this polynomial. I'm going to call this P of lambda. So set P of lambda equal to 0. So this implies 1 minus lambda raised to 3 equal to 0. And this implies, of course, that the only solution is lambda equal to 1. So now, yes, I can do this. The algebraic multiplicity in this case makes reference to the multiplicity of this solution for this polynomial. I mean, algebraic multiplicity is number of times we have like a repeated the solution in the polynomial. In this case, we have 1 minus lambda raised to 3, so this root has multiplicity equal to 3. Algebraic multiplicity equal to 3. Okay? Now, this is as for the algebraic. What about the geometric? For the geometric, we have to find the corresponding eigenspace. So, we need to find the eigenvector. Finding eigenvectors. And remember, we do this, we look for a vector x, in this case equal to x1, x2, x3, that is not the zero vector, such that a times x is equal to lambda x. Or what is the same? A times x equal to, in this case, lambda, notice, is equal to 1. So it would be 1 times x. That is only x, right? So this implies the matrix 1, 1, 0, 0, 1, 1, 0, 0, 1 times x1, x2, x3 should be equal to x1, x2, x3. And this implies we will have the equations x1 plus x2 equal to x1, x2 plus x3 equal to x2, and x3 equal to x3. I am multiplying only, I only doing the multiplication, all right? 1 times x1, x1, plus 1 times x2, x2, plus 0, x3, so we put nothing. 0, no x1, 1 x2, 1 x plus x3. No x1, no x2, 1 times x3, x3 equal to x3. And this implies, notice if we simplify this, subtract x1 here, x2 here, and x3 here, we're going to have x2 in the first equation, x2 equal to 0. In the equation number 2, x3 equal to 0. And in the equation 3, 0 equal to 0. So the solutions are x equal to x1, x2, x3 equal to, notice, all of them, they are 0, x2 and x3. The x1 is not here, so it is a free variable. x1 can have any value. So in this case, we have x1, 0, 0. Or what is the same? x1 times the vector 1, 0, 0. Or what is the same? Remember, this vector, the canonical, is part of the canonical standard base. So 1, 0, 0, or what is the same? x1 times the vector e1. So what is the dimension, the subspace? Since it has only one linear independent vector, the dimension for this, then E lambda is the subspace of all the x such that x is equal to x1 times 1, 0, 0. One basis for E lambda is precisely E1, 1, 0, 0. So what is the dimension for this subspace is 1. then the dimension for E lambda, in this case E1, is 1. And this is the geometric multiplicity of lambda equal to 1 is only 1. Other example, determine the geometric and algebraic multiplicity of the matrix A equal to 1, 1, 0, 0, 1, 0, and 0, 0, 1. First, the characteristic polynomial. Again, the characteristic polynomial, remember, is the determinant for A minus lambda times the identity with size 3. In this case, because this has size 3 by 3. So it's going to be the determinant of what? Determinant of 1 minus lambda, 1, 0, 0, 1, 0. I'm sorry, 1 minus lambda here. 1 minus lambda, 0, 0, 0, and 1 minus lambda. So again, this is going to be 1 minus lambda raised to the 3. Why? Because we have another triangular matrix. When you have a triangular matrix, the determinant is only the product of the numbers in the main diagonal. So this is, again, algebraic multiplicity of lambda is 3. And we said to find lambda, set the polynomial equal to 0. Let's call this P of lambda. So set P of lambda equal to 0. We have 1 minus lambda raised to the 3 equal to 0. And this implies, of course, lambda equal to 1. So this eigenvalue has multiplicity, algebraic multiplicity of equal to 3. But what is its geometric multiplicity? For this, we need to find the eigenvectors and define or create or to have the subspace. So notice finding eigenvectors. So we look for x equal to x1, x2, and x3 such that that is not the zero vector. such that a times x is equal to lambda times x, or remember that in this case lambda is 1 times x, or what it is saying, x only. So the same as before, this is going to imply 0, 1, 0. No, 1, 1, 0. 1, 1, 0, 0, 1, 0, and 0, 0, 1 times x1, x2, x3 equal to x1, x2, x3. And if you get the equations here, we're going to get, notice, do the multiplication. This is going to be the first equation, x1 plus x2 equal to x1, x2 equal to x2, and x3 equal to x3. So you solve for this. I mean, if you, again, subtract for equation 1 x1, for equation 2 x2, and for equation 3 x3, we're going to have x2 equal to 0, 0 equal to 0, and 0 equal to 0. So this means the solutions have the form x equal to x1, x2, x3. Notice in this case we're going to have two free variables because they don't appear here, so that means that x1 and x3, they are free variables. So the solution, they have the form x1, x2, x1, 0, and x3. You see, because x1 and x3, they are free variables. They don't show up here. The only basic variable is x2. But notice one possible base for this can be expressed as x1, use the canonical standard base, times 1, 0, 0, plus x3 times 0, 0, 1. You see? So we say that in this case, E lambda is equal to all the vectors such that the vectors, they have the form x1 times 1, 0, 0 plus x2 times 0, 0, 1. You see? So then one basis for this E lambda is precisely, notice how we have, these are the E1 and E2. So this is the same as x1 E1 plus x3 E3. So this means that one base is E1 and E3. One, 0, 0, and 0, 0, 1. So this basis has two elements. Then the dimension of E lambda is 2. And this is the same as geometric multiplicity. So to find the geometric multiplicity, you will need to have well-defined all the solutions for the given eigenvectors, and you will have to find a basis for that. Once you have found the basis, count the number of elements in the basis, and that number, the dimension, is going to be the geometric multiplicity. All right. One more concept, similar matrices. The matrices with size n by n matrices A and B are said to be similar if there is an n by n invertible matrix S such that B is equal to the inverse of S times A times S. Similar matrices. Two matrices A and B are similar if we have a matrix that has an inverse and such that this equation is possible. Example. Notice, if I have A equal to -1, 2, 2, 3, 1, B equal to -5, -3, 6, and 5, and the matrix P equal to 2, 1, -1, and 0, then first, notice how this matrix P is invertible. It has an inverse. Why? Because the determinant of P is different from 0. It's 2 times 0 minus -1 times 1, that this is equal to 1. So we can find the inverse. We can use one of the methods we saw before. That is, the inverse is 1 over the determinant of P times dA, -B, -C. And remember that this makes reference to the matrix P. This is A, this is B, this is C, and this is D. So in this case would be 1 over 1 times 0, 2, -1, and 1. And this is only 0, -1, 1, and 2. So I have the inverse for P. P, B, and A. So that, notice, I have to prove that A is equal to P times B times P inverse, or P inverse times P. I mean, this equation can be written the same way. B is equal to S times A times A inverse. I'm sorry, I'm using a different symbol, right? I'm sorry, I can change that. This is S. S, so this has to be S inverse. So notice that S inverse, S times B I'm trying to show this equation, so I'm sorry, S times A is equal to S, that is 2, 1, negative 1, 0, 2, 1, negative 1, and 0, times A, that is negative 1, 2, 3, 1. This is equal to negative 2 plus 3. Here, 1 plus 0. Here, 4 plus 1. And finally, negative 2 plus 0. So this becomes 1, 5, 1, and negative 2. Next, what is SA times the inverse? Is going to be this matrix 1, 5, 1, negative 2 times the inverse for S, that is 0, negative 1, 0, negative 1, 1, and 2. 0, negative 1, 1, and 2. And this is equal to 1 times 0, 0, plus 5 times 1, 0 plus 5. Here, row 1, column 2, negative 1 plus 10. And here, 0 minus 2. And here, negative 1 minus 4. And this is supposed to be equal to 5, 9, negative 2, and negative 5. This is supposed to be equal to the matrix So no, I'm sorry, I think I did a mistake. Let me check if I can find the mistake. We will show, I'm sorry, S inverse times A times S is equal to B. Yeah, this is one, I'm sorry. Yeah, because I did the multiplications in the other way. I use S times A times S inverse, and that's not going to work. It should be like this. S inverse times A times S. So yeah, in this way it should work. Notice. S inverse times A is equal to 0, negative 1, 1, 2. Zero, negative 1, 1, 2 times A. A is negative 1, 2, 3, 1. So this is going to be 0 minus 3, 0 minus 1, negative 1 plus 6, 2, row 2, column 2, 1 times 2, 2, plus 2 times 1, 2. row 1, column 1, 0, 0, negative 1 times 3, negative 3, row 1, column 2, 0, negative 1, row 2, column 1, 1 times negative 1, 2 times 3, 6, row 2, column 2, 1 times 2, 2, yeah, it seems to be okay. And this is equal to negative 3, negative 1, negative So it seems like the Apple Pencil stopped working. So let me see if I can close this. Oh yeah, now it worked. So it should be negative 3, negative 1, 5, and 4. So this is S inverse times A. Now I'm going to do S inverse times A times S. What is it saying? Negative 3, negative 1, 5, 4 times S. Notice that S is 2, 1, negative 1, 0. 2, 1, negative 1, and 0. So this becomes row 1, column 1, row 1, column 1, negative 3 times 2 is negative 6, plus negative 1 times negative 1, plus 1, row 2, column 1, 5 times 2, 10, plus negative 4, row 1, column 2, negative 3 times 1, negative 3, negative 1 plus 0, row 2, column 2, 5 times 1, 5, plus 4 times 0, plus 0. So this becomes negative 5, negative 3, 6, and 5. And notice this is the matrix B. Yeah. So here we have that S inverse times A times S is equal to B. You see that? So we have this matrix is expressed, or what is the same, notice this is equivalent to A is equal to SB times S inverse. Yeah, I confused the order of the matrices. That's why I didn't have the result that I wanted before. But yeah, this proves A and B are similar. So related to this, we have the next theorem. If A and B are similar, then first one, the determinant of A minus lambda times En is the same as the determinant of b minus lambda times in. So this means what? A and b have the same characteristic polynomial. Then they have the same eigenvalues. And the eigenvalues of A and B have the same algebraic multiplicity. Only the algebraic. It doesn't say anything as to the geometric, right? All right, new definition. D of size n by n is a diagonal matrix if all its entries are 0, except on its main diagonal. So a diagonal matrix is a square matrix, of course, but it has only zeros in the main diagonal. For example, 5, 0, 0, and 6. I mean, all the numbers are 0 except the ones in the main diagonal. For example, this one, 1, 0, 0, 0, 1, 0, 0, 0, 1. The identity matrix is a diagonal matrix. This one as well, 2, 0, 0. So notice the characteristic of a diagonal matrix is that in the main diagonal the numbers are not 0, but in the rest only zeros. So this is a diagonal matrix. Only zeros except in the main diagonal. So definition. We say A of size n by n is diagonalizable if A is similar to a diagonal matrix D. So we say A is diagonalizable if A is similar to a diagonal matrix D. And the concept of similar, remember this one? Yeah, if we have inverse matrices, if B and A are related in this way by an inverse matrix. All right. Theorem. A is diagonalizable if and only if A has a set of n linearly independent eigenvectors. And other theorem. If A of size n by n has n different eigenvalues, then A is diagonalizable. So, in other words, for a matrix to be diagonalizable, it's enough if we can show that it has n different eigenvalues. For example, if A is with size 2 by 2, if we have two different eigenvalues, then for sure we can find a diagonal matrix similar to A. And the same happens if A is with size 3 by 3 and so on. So let's see one example to finish this. Example. Show that A is diagonalizable. We have A equal to 5, negative 6, 3, and negative 4. So first, of course, we need to find the eigenvalues. Remember that the eigenvalues are given by the determinant of A minus lambda times the identity with size 2, because this matrix has size 2 by 2, or what it is saying, the determinant of the matrix 5 minus lambda, negative 6, 3, negative 4 minus lambda. And this becomes equal to 5 minus lambda times negative 4 minus lambda minus negative 18. So this becomes 4 times negative 5, negative 20, 4 times negative lambda minus 5 lambda plus 4 lambda plus lambda squared plus 18. So we have lambda squared minus lambda minus 2. remember this, how do we call this? This is the characteristic polynomial. So set this polynomial equal to 0. And then we have lambda squared minus lambda minus 2 equal to 0. And here we can apply the technique, give me two numbers such that when you multiply them you have -2, and when you add them you have -1, the coefficient for lambda. So I think those numbers, they are lambda minus 2 and lambda plus 1 equal to 0. So this implies, of course, lambda, I'm going to label this as lambda 1 equal to 2 and lambda 2 equal to -1. By now we have this eigenvalues. Next, of course, we have to find the eigenvectors. Finding the eigenvectors that we have done before. I mean, all the possible eigenvectors. So remember to do this. Let's do it first for lambda 1 equal to 2. So we look for a vector x in the form x1, x2, such that a times x is equal to lambda 1 times x, so what is the same? 2 times x. So we have this, the matrix is 5, -6, 3, -4, times x1, x2 equal to 2 times x1, x2, and this implies two equations, 5x1 minus 6x2 equal to 2x1, 3x1 minus 4x2 equal to 2x2. And if we isolate, remember we have to subtract 2x1 here and 2x2 here in the equation 2, for 2x1 in the equation 1, 2x2 in the equation 2. So we're going to have 5x1 minus 4. No, I'm sorry. This is 5 minus 2 is 3x1 minus 6x2 equal to 0. And now here subtract 2x2 is going to be 3x1 minus 6x2 equal to 0. So notice again we have the same equation. So this means we have infinitely many solutions. So the reduced echelon form, you can verify. Again, you can use the online calculator I recommended before. It's going to be 1, -2, 0, 0, 0. So this is x1, this is x2. Basic variable is x1, free variable is x2. So this means that the eigenvectors in this case, they have the form x equal to x1, x2. They are the same, so the free variable is x2, so x2, x2, or what is the same? X2 times x1, times 1, 1. And now from here, you will have to choose one eigenvector. We have infinitely many eigenvectors in this case. We have one for each value of x2, but you will have to choose only one. Which one? The one that you want. We will set x2 equal to 1, and this implies that I'm going to label this by x1 here, x1 is equal to 1, 1. So by now, we have this eigenvector here. Eigenvector for lambda 1 equal to 2. Now let's do it for lambda 2. Lambda 2 is equal to -1. -1. So the same as before, we look for x equal to x1, x2, that is not the zero vector, such that a times x is equal to lambda 2 times x, or what is the same, 1, -5, -6, 3, -4 times x1, x2 equal to, this is -1 times x, or equal to -x only. So this is -x1, -x2. So the equations here are 5x1 minus 6x2 equal to -x1, 3x1 minus 4x2 equal to -x2. So again, subtract from the equation 1, add x1, and in the equation 2 add x2. You will have 6x1 minus 6x2 equal to 0. And in the equation 2, we will have 4x1 minus 4x2 equal to 0. And again, compute the reduced echelon form. You will see that we have the same equation, so we reduce echelon form is going to be 1, -1, 0, 0, 0, 0. So this is x1 and this is x2. So again, the same as before, x1 is equal to the basic variable and x2 is free. x2 is free variable. Then our vector is x1, x2, that is the same as x2, x2, so it's equal to x2 times 1, 1. The same as before, here you will have to choose one eigenvector. So, I'm sorry, I think I did a mistake here. Notice 1 minus 2, 0. So this is 1 equal to 2x2, I'm sorry. So x1 is 2x2. So this should be, I'm sorry for this, it should be 2, 1. So, but this doesn't change this. We set x2 equal to 1. So the difference is that the vector is going to be 2, 1. Yeah, I'm sorry for this. So 2, 1. Yeah, because this should be 1 equal to x. This implies x1 equal to 2x2. You see, if you solve here. All right. Now for this one, let me see if I don't have any mistakes. So in this case, we have x1 equal to x2. Yeah. x1 equal to x2, so no problem here. So x1 is equal to x2, so then we have x2 times 1, 1. Now again, we have to choose one vector, one value for x2. In this case, for the free variable that is x2, choose any value that you want. In this case, I will choose the easiest value in my opinion. We will choose x2 equal to 1. Then I'm going to call this x2. x2 is going to be 1 times 1, 1 is going to be 1, 1. You put it in yellow. x2 is going to be equal to 1, 1. And this is eigenvector for lambda 2 equal to what? Equal to -1. Yeah. All right. So once you have all of this, notice how to diagonalize the matrix A. We wanted to diagonalize A. This is find a diagonal matrix D and an inverse matrix S such that A is equal to S times D times the inverse of S. How to find these matrices S, D, and S? Well, once you have S, you will have the inverse. Here, S is going to be created by the two eigenvectors that we found for each eigenvalue. I mean, in this case, it's going to be from x1 and from x2. I know this is they have two components, so this means that the matrix is going to be x1, remember, is 2, 1, so it would be here 2, 1, and x2 is 1, 1, so it will be here 1, 1. There you have. This is the matrix S. And notice this matrix is going to be invertible because the determinant is 2 times 1 is 2 minus 1 is 1, so it has an inverse. And how to create the matrix D? the matrix D has to be equal to, it's a diagonal matrix, lambda 1, 0, 0, and lambda 2. Be careful here. When you set up this matrix D, I mean, how do you know what are the eigenvalues that you have to label as S1 or as lambda 1 or lambda 2? Well, it's up to you, but I have decided to label lambda 1 as 2 here and lambda 2 as -1 here. But how it is reflected here when I set up the matrices? Notice, if I call this lambda 1, that means that D is equal to lambda 1 is 2, 0, 0, and lambda 2 is -1. So my first one here was lambda 1, so I have to put here first the corresponding eigenvector for lambda 1. You see that? If I had chosen lambda 1 as -1, I would have to put this vector x2 here first. That okay? So be careful with that. No matter how you label lambda 1 or lambda 2 for the eigenvalues, but once you have decided what is the first one and the second one, when you create these two matrices, you have to put the corresponding eigenvectors and eigenvalues. Since my first one is lambda 1, then the corresponding eigenvector has to be x1. The second one is lambda 2, the corresponding second eigenvector has to be x2. And once you have this, you can verify that A is equal to S times D times S inverse. That okay? And there you have a diagonal matrix. A is a diagonal matrix. I mean, what is the purpose? One of the application for a diagonal matrix, the next one. Since A is equal to S times D times S inverse, notice that what happens if I multiply A times itself? I mean, I compute A squared. There will be S D times S inverse times S D S inverse. So this would be, notice, S inverse times S would be S D S inverse times S times D times S inverse. So this is equal to S times D times the identity matrix with size, in this case size 2, times D times S inverse times S inverse. But when you multiply the identity matrix times any matrix, it's the same matrix. So we will have S times D times S inverse, or what is the same, S times D squared times S inverse. So notice, in this case, A squared is equal to S times D squared times S inverse. In other words, when you multiply A squared, when you have a diagonalizable matrix, if you want to raise this matrix to square, it's only S times D squared times S inverse. And you say, well, I have to raise D to square as well, right? Maybe that's going to take so much time, but no, because well, first let me finish this. In the same way, it can be shown that A raised to the K is going to be equal to S times D raised to the K times S inverse. But note, for example, in this case for D, our matrix D is 2 and -1, 2, 0, 0, -1. What happens when you raise D to the square? We have 2, 0, 0, -1, and 2, 0, 0, -1. So this becomes only 4, 0, 0, and 1. Or what is the same? 2 raised to the square, 0, 0, and 1, and -1 raised to the square. So in other words, we continue with this pattern. You can check that a diagonal matrix raised to the any power that is a natural number is going to be only raise the corresponding entries in the main diagonal to the power. I mean, it's going to be 2 raised to the k times negative 1 raised to the k, and the rest 0 and 0. So in this case, this matrix A raised to the k would be the matrix S times D raised to the k, that is 2 raised to the k, 0, 0, negative 1 raised to the k, times the inverse. Or what is the same? S. Well, I mean, I don't have the inverse, but I don't want to waste time on that. So you can raise any matrix. I mean, well, you can raise the diagonalizable matrix to any power in a very simple way. Why? Because you have to raise 2 to the k, negative 1 raised to the k, and once you have done this, multiply times S inverse. But with that, you are computing a raised to any power. For example, a to the 1000, raise this to the 1000, this to the 1000, and then only multiply the resulting matrix times S and then times S inverse. And there we have that. So that's one of the application for diagonalizable matrices. All right, that's all by now. See you later.